to introduce how can we come up with this similar equation by the potential method and solving the ODE like that. So so as before, we have actually derived the simple RLC circuit with some initial condition without this AC source, but now we have an AC source here. So the only difference is only we have G of t here. So but actually I can still repeat the procedure again quickly so that you have one more chance to get used to how to use the potential method to write our the equation governing the circuit. So so let us define this is VR, this is VC, this is VL. So using the KVL, we can have E. Of course, E actually equals to EM cosine omega dt. So this is actually a sinusoidal. Yeah. So E is only a notation for this time domain function. Okay, so E. So when we go from this point to this point in this way, so we have E. But in the other direction, we can go to this way, and this way. So we have from here to here, we have VL. And then from this point to this point, we have VC plus VC. And then from this point to this point, we have plus VL. Okay, so still we have I equals CD VC dt, and also we have VL equals LDI dt. So we can simply plug in this equation into here. So we have LCD 2 VC dt 2. So take the second derivative. We just plug this into here, which means that we take the derivative and C is a constant. So we have L and C, and then the second derivative of this term of VC. Okay, so and also VR equals R times I, which means we also plug in this into here. So we have RCD VC dt. So we can now plug in this this one and this one into here and here. So we have let me see, LCD 2 VC dt 2 plus RC dVC dt plus VL equals EM cosine omega dt. So we have D2 VC dt2 plus we just divide LC on both sides, so we have R over L dVC dt plus 1 over LC VC. Should be VC because this is VR, this is VL, this is VC. So this should be VC equals EM over LC cosine omega dt. Yeah, actually we hope to have a ODE with the unknown function to be I, so we can, let's say, multiply both sides by C and take the derivative. So for both sides, we just multiply by C and take the derivative on both sides. Add on here, so we have C d3 VC dt2 plus RLC d2 VC dt2 plus 1 over LCC dVC dt equals. So on the right side we have EM over L. C and C will be cancelled, and then we take the derivative. So it becomes minus sine omega dt. And of course we still need to take the chain rule, so we have omega d here. And of course we have I equals C dVC dt. So we have d2 I dt2 plus R over L di dt plus 1 over LC I equals minus omega d EM over L sine of omega dt. So we get this ODE, which is related to the current, So for the phasor, as I mentioned, we don't really care about the homogeneous solution. Of course, if you really need to find the complete solution, you need to find the homogeneous solution first, and then you try to find the particular solution. Okay, so far we have this one, and yeah, of course you need to find the homogeneous solution, and then find the IC of t, and then second you need to find the particular solution, IP of t, and then the complete solution will be just add them together. But suppose t is large, then IC of t will tends to 0. IC of t will tends to 0, because as much as you know, if we only have this one without the right hand side, the solution will be nothing but let me see, will be this one. Yeah, the solution will be this one. Yeah, actually you can write it as I, because you take dq dt and it will be the current. And actually we have this exponential function with a negative exponent, which means that when t is large enough, this term will tend to 0. So, and this response only related to the system itself, and as much as it will vanish, it will tend to 0 when the time pass. So finally, the solution will only be determined by the input. Will only be determined by the input. Yeah, which means let's say this is the g of t. So which means I of t will be dominated by the by g of t when t is large. T is large. So a phasor, the phasor is a method to just give through the homogeneous solution, and it find the particular solution directly. So in this case, if we really try to solve this one, solve this ODE with this g of t, this is a sinusoidal, which means that we will assume our particular solution, or actually the steady state, to be like a cosine omega dt plus d sine omega dt. Because this is just a sinusoidal function, so we need to assume cosine and sine with the same frequency. Yeah, and of course we can just substitute this one into the original equation, and wow, it will be quite long. Actually, you can just plug in this one into this equation. You can just plug in this equation, and then finally you will get d to be, this is just, so you just plug in this here, here, and here. And of course you need to take the second derivative, the first derivative, and the original function, and then you try to simplify it. So it is not difficult at all, but it is just lengthy. And finally you can find that d to be Em times R squared plus omega d L minus omega d 1 over omega d c. Omega d c, something like this, and then take the square. And A should be A, B here. Should be A and B here. So actually you can just solve A and B to be like this. Em times minus omega d L minus 1 over omega d c, and over R squared plus omega d L minus 1 over omega d c squared. So as much as we have this A and B, and you can find that A and B is actually the real part and the negative imaginary part of the phasor. Yeah, of course the phasor is like this expression. I, we call that I is actually Em over R plus J 1 over omega dl omega d L minus 1 over omega dc, something like this. But if you just multiply the denominator and the numerator by the complex conjugate of the denominator, then you'll find actually you can just multiply it by this R minus J omega d L minus 1 over omega dc, and then in the numerator you also multiply it by this factor. Yeah, then you can see that this is A plus B, this is A minus B, so it becomes A minus B squared. And A minus B squared is R squared, which is this R squared, and then this square minus this term square. J squared is minus 1, so we have plus this term square, this whole term square to be in the denominator, and the numerator, the real part will be this one, this A will be this one, and then for this one minus this part will be here, So we finally find that A plus A cosine omega d plus B sine omega dt is actually this one. So you can use the ODE method to find the similar expression, but as you can imagine, if we have A, B like this, so it turns out that the phasor will be A plus JB, will be the phasor. And of course, this is a complex number in the Cartesian coordinate. If we just convert it to polar coordinate, it becomes R exponential to J phi, something like that. So R will be the square root of A squared plus B squared, square root of A squared, B squared. And then phi will be the arctangent B over A, which is actually the same as this expression. So next, it should be A minus JB, A plus JB, A plus JB. Yeah. So let's see a sample problem, so that you may not feel so as difficult as I derive. Yeah, so here we have RLC to be these values, and the FD is 60 Hz, EM to be 36 volt, which is the same as the previous sample problem. So what is the amplitude of the current phasor I? So the current phasor I will be, let's say, we have Z to be R plus J omega d L minus 1 over omega dc, like this. So we can just plug in the number. R is 200, and C plus J omega d 60 Hz, so omega d is 120 pi, and then times 230 milli, and then minus 1 over 120 pi, and then C is 15.0 times 10 to minus 6. So this number is 200 minus J 90.13. And we will say that this is capacitive, as the imaginary number is a negative number. So if the imaginary number of the Z is larger than 0, then we will say Z is inductive. And if imaginary number of Z is smaller than 0, then Z is capacitive. capacitive. As much as you know, the Z of an inductor is J omega L, so it will be a positive value. And the impedance for the capacitance will be 1 over J omega C, which means that it is actually minus omega over, minus J over omega C. So it will be a negative imaginary part. So we will say if Z has a positive imaginary part, then we will say Z is inductive. It works like a inductor series with a resistor, and if the imaginary part of Z is smaller than 0, we will say Z is capacitive. It's just like the capacitor series with a resistor. So it's about the steady state. We don't really care about the transient response. We don't really care about the homogeneous solution. Then for the steady state, we only care about the difference between the impedance of the inductor and the capacitor. So part of them will be cancelled because some of it has a positive imaginary part, some of it will have a negative imaginary part, so that it might be partly cancelled or even perfectly cancelled. Okay, so this is the impedance of this circuit, and the amplitude will be I, the absolute value of phasor I, which is, or you can find the phasor first. The phasor is nothing but the phasor of V over C. Of course, the phasor of V will be 36 because it is like 36 cosine omega dt, something like this. Actually, like this. EM is just the amplitude. The whole E is like the sinusoidal function, and of course V is nothing but 36 over 200 minus J 90.13. So you can just you can actually try to simplify it by multiplying this by 200 plus J 90.13, and then also you can multiply it by 200 by J plus J 19.13 like this. Then you can just simplify it, and then it becomes something like A plus JB. But actually you can just find the amplitude by taking the absolute value, and then you can just take the absolute value of this one, which is 36, and then the absolute value of the denominator will be 200 square plus 90.13 square, and then take the square root. So this number is 0.164 ampere. So this is the amplitude. This is the amplitude of the current phasor. Actually, you don't necessarily remember this this one, so it looks so horrifying, but yeah, so you can just plug in the number, and then it's just a complex number. The complex number. So this is the part A. This is the amplitude of the current phasor, and next is the phase of the current phasor I, which means we need to find phi. Yeah. Yeah. So so phi will be nothing but arctangent omega d L minus 1 over omega d C, and then over R. Which means it is nothing but this part is minus 19.13, minus 19.13. Yeah, so it is arctangent minus 19.13 over R is 200. R is 200. So you can just press the calculator and then you'll find that this is minus 24.3 degrees. Or you can write it in radian. It is minus 0.424 radian. Yeah, you can just change it by minus 24.3 degrees over 180 degrees times pi, and then it becomes the radian. Yeah, so this is the phase. This is the phase. Which means that we don't really need to solve the ODE, because solve the ODE will be quite tedious. Actually, you need to assume this particular solution and then plug it back. I just skip all the lengthy procedure because it is quite a lot of work to work out these two. So you can see that you need to write two equations and then you find that the solution will be like this. So you can simply imagine the process take quite a lot of time to work it out, but it is not difficult at all. And in this case, we only need to use this expression. So finally, we can find that. Finally, we can find that I is nothing but this one, which means that I has the expression as I cosine omega dt minus 5, something like this. Which means that I is actually the amplitude and this is the phase. We already we are defined it out. So I of t is nothing but this 0.0164 cosine omega d is 120 pi t minus we can just use the radian here, so we can just write plus, because this is a negative sign, we also have a negative sign here, so it is 0.424 like this, and then A. Of course, this is not asked by the question, but actually, after finding the phase and also the amplitude, we can directly write it out write the time function of the current out like this, just by plugging in the amplitude here and the phase negative of the phase here. Yeah. Okay, any questions? Okay, so next we talk about the power in the alternating current circuit. So this is somehow related to the lab report, I should say. Yeah, and yeah, someone has asked me about the measurement result, and it turns out to be quite a lot of difference. And yeah, actually, the measure value from the multimeter should be the RMS value rather than the amplitude. And yeah, here we talk about difference between them. So yeah, this is the instantaneous rate of power dissipated. So before we only concern is the DC. So the voltage and the current are constant and the power also constant. So we only just calculating some numbers, then that's fine. But here, as much as we have the AC source. So this alternating current in short form is AC. So you should familiar with this short form, because when we use the electricity from the socket, it is some sort of AC source rather than DC source from a battery. So now, as much as we have an AC source, which means that the waveform is a sinusoidal, no matter if the voltage, the current, the power will also be the sinusoidal wave. And yeah, and the loading is not necessarily resistive. So the phase, there may be some phase difference between the voltage and the current. And of course, we can still calculate the instantaneous rate of power dissipated by using this equation, which we are familiar with. So which is P equals I square R. And as much as we know, I of t is square absolute value of the phasor, and then sine of, let me see, let me see, sine, oh, this is sine, this is sine, oh, this is sine, so, oh, then it is, so, yeah, this is sine, and yeah, sine of omega t minus phi. So I square will be this one square times r, and then sine square of this term. So of course this is a sine square, which is, if you still remember, sine square of x is 1 minus cosine of 2x all over 2. So it's still some sort of a cosine, but we only shift it up. Yeah, and and of course the P average can be calculated by this integration. So this is a square, so it is all the way a positive number. It is all the way the positive number, because if we only concern the average value of I, it will be 0, because half of it will be positive, half of it negative, and they are symmetric. So when we take the average value of the current or the voltage, then it will be surely 0. But here, after taking the square, then it will be all the way positive, and then we try to take the average value. We try to take the average value of the instantaneous power. The instantaneous power, instantaneous in Chinese is 瞬时, which means for every moment. So it is like going up, going down, going up, going down. So some of the time the instantaneous power is 0. Some of it the instantaneous power is maximized as this one is 1. And so it will be I square over R, but it only appears for just a fraction of time, just a moment, and it will be mainly between this 0 and 1, and then multiplied by this factor. And the interesting part is that when it is when we're taking the average, it is only half of it. So from the figure we can simply imagine, because you can just move this part into here, so it will be just a square. It's just a constant. So we move this part into here, so it becomes a rectangle. So you can simply imagine it is just half of it. And of course, if we need to do it carefully using the mathematics, we will just integrating this signal for a period from 0 to t. And of course, we have a 2 pi omega d equal times t. Omega dt no 2 pi, should be 2 pi f, should be omega dt should be 2 pi, should be 2 pi, something like this. And yeah, we can do the integration, and we don't necessarily need to care about the phase. We don't necessarily need to care about the phase. So for this one, it is nothing but this. So we have a 1, which means that we actually take the integration for this part. Integration for this part, because this is just a constant. As much as we integrate this part and then finally we multiply by this factor, then it will be the average power. But first, we only care about this, the average of this part. So the average of this part divided by the total of time. So this is just like the average value of sine square for a period. So we need to divide it by 1, divide it by t. So here, sine square is 1 over 2 times 1 over cosine 2 of this omega dt. And in that case, this one is nothing but t. This one is nothing but t. So t and t will cancel. This part will be 0. This part will be 0. This part is just like 1/2 omega d, and then sine of omega dt. We just don't need to care about the phi, and then we plug in t and 0 here. So if we just plug in t to here, omega dt is 2 omega dt is 4 pi. So this is 4 pi. So sine of 4 pi is 0. And if we just plug in t to be 0 here, sine of 0 is also 0. So this term will be 0. So we find that the average value of this term is 1/2, which means that the average value of the power will be 1/2 times I square R, which is this one. This one is important. So we can try to separate these two into here, because we have I squared. So we make it like I over square root of 2, and then the whole term take the square. So this is called the root mean square value. If we just take the absolute value, it is the amplitude, which means that if it is I, so this is now this, if this is I of t, so this value will be absolute of I, and the average value, which means that if we need to consider the root mean square value, it is something like this one, which is the absolute value of phasor of I over square root of 2. This is what we call the I root mean square, the root mean square value. If we consider the root mean square value, we can use the original. So now we define I root mean square to be I over square root of 2. So it is like I RMS square R, which will be something like this. If we only use I square, we need to consider to divide this term by 2. Then it looks like sometimes we divide by 2, sometimes we don't. But here, when we consider DC power, then we all the way use I square R. And for AC, we will use the root mean square, so that when we plug in I root R RMS and then take the square out, then it will be the average power. And of course, we also define this is root mean square for the I. and also the root mean square for the voltage. So also we can write it as something like, yeah. So we have this expression. We have a cosine factor here. We have a cosine factor here rather than only having I RMS V RMS, because the I and V doesn't necessarily to be in phase. If they are in phase, then phi to be 0, then this factor is 1. But sometimes they are not. So in that case, the average power may not be just I RMS times V RMS. Of course, here we only consider the R, I square RMS R. But of course, the complex power will be the phasor of V times the phasor of I. And if they are not should have a conjugate here. And if they are not in phase, then this is a complex number. Then it will be look like I RMS square R plus J times I RMS square X. Here X will be like J, sorry, not J, will be like omega d L minus 1 over omega d C, something like this. So this is the imaginary power, which is some power stored in the inductor or the capacitor. Yeah, and now as much as there may be some phase difference, we need to multiply by this factor called the power factor, I think, which is cosine of phi. And you can simply imagine that if phi is 0, then this term is 1, then P average is I RMS V RMS. So P average is maximized. If phi is 90 degree, then cosine 90 degree is 0, then P average is 0. Because sometimes it looks like one is sine, one of it is cosine. So one of it is like this. Yeah, like this. Yeah, it's like this. So some of it is negative multiply positive. Sometimes it is positive multiply positive, and then when you take the average and when you multiply them together and then take the average, then finally it will just cancel out, because you can simply imagine if you have sine of x multiply cosine of x, it is nothing but 1/2 sine of 2x, and then you integrate it over a actually 2 periods, then it will be 0. So actually this is the power, average power related to the AC circuit. It is not IRMS, VRMS anymore. It will be IRMS, VRMS multiplied by this power factor. And if you use the R to calculate it, it will be the P average. Or actually you can use IRMS squared times Z. It will be this case, because Z is R plus JX. So it will be IRMS R. This is the real power. Oh, this is the imaginary power. Okay, let's take a look at maybe let's have a 10 minutes break.